Hi everyone, I'm Dan Fullerton and I'd like to welcome you back to educator.com. This lesson is on magnetic fields and properties. Our objectives are going to be to explain that magnetism is caused by moving electrical charges, describing the magnetic poles and interactions between magnets, drawing magnetic field lines, recognizing magnetic permeability and magnetic dipole moment as properties of matter, calculating the force exerted on a charge moving through a magnetic field, and explaining the operation of a mass spectrometer. So let's start by talking about what magnetism is. Magnetism is a force caused by moving charges. Magnets are dipoles. They all have a north and a south. You can't have a north without a south, or a south without a north. There are no magnetic monopoles. Like poles repel, and opposite poles attract. Now, magnetic domains are clusters of atoms with electrons spinning in the same direction. Atoms have those moving electrons, therefore they're magnetic. Same thing here, as we have magnetic domains, electrons spinning in the same direction, we get a net, what we call magnetic domain. If we have random domains where they're all pointing in random directions, you don't have any net magnetic field. But if you can get some of those domains to point in the same direction, you can end up creating a strong magnet because you have a net magnetic field all pointing in the same direction. Now, to start off with, which type of field is present near a moving electric charge? Well, not an electric field only because a moving charge has a magnetic field, and not a magnetic field only because you still have the electric field. So what type of field is present? You must have both an electric field and a magnetic field. You have the electric field because you have a charge, and because it's a moving charge, you get a magnetic field. Now, magnetic field strength is a vector quantity. It's given the symbol capital B typically, and its units are Tesla, capital T, where 1 Tesla is equal to 1 Newton second per Coulomb meter. Now, magnets are polarized. Each has 2 opposite ends. You have a north with a south. The end of the magnet that points toward the geographic north pole of the Earth is called the north pole of the magnet. Now, there are no magnetic monopoles. Again, you can't have a north without a south, or a south without a north. Magnetic field lines make closed loops and run from north to south outside the magnet. Very similar to electric field lines, magnetic field lines run from north to south. They continue through the magnet, but outside the magnet, they always run from north to south. Now, the density of the magnetic field is known as the magnetic flux. So you have more magnetic flux in a region like this than you do in a region like this because the magnetic field lines are closer. And the magnetic field lines show the direction the north pole of a magnet would tend to point if it was placed in that field. Now, because we're going to have to deal with 3 dimensions as we answer some of these problems and analyze some of these situations, we need a way of representing that on a page that's only 2-dimensional. So up, down, left, and right on the page are pretty easy. But how about if you want to go out of the page? Well, to represent a vector pointing out of the page or toward you out of the screen, you would put a dot, or sometimes you'll see it as a dot with a circle around it. Imagine that's an arrow. If the point is coming toward you, what you're going to see is the point. So it's coming toward you or out of that plane. If it was going away or into that plane, you would see the fletchings on the arrow. So those are typically shown as X's or X's with a circle around them. That would be pointing into the plane here or coming out, well, going into your screens at home. So let's take a look at another example where we have lines of magnetic force. The diagram below shows the lines of magnetic force between 2 north magnetic poles. At which point is the magnetic field strength greatest? Well, that's going to be where we have the densest lines, or over here at B. Densest lines, therefore you have the greatest magnetic flux. The density of the magnetic field, or B field, is known as magnetic flux. And it gets the symbol, a capital Phi, magnetic flux. Sometimes you'll see that written as Phi B to show that it's magnetic, or even Phi M for magnetic. Let's take a look at an example where we look at forces between bar magnets. The diagram below represents a 0.5 kilogram bar magnet and a 0.7 kilogram bar magnet with the distance of 0.2 meters between their centers. Which statement best describes the forces between the bar magnets? The gravitational force and magnetic force are repulsive. Well, if we have like poles, they're going to repel, so the magnetic force is going to repel. But gravity can never repel. Gravity can only attract. Can't be A. Gravitational force is repulsive. No, gravity still can't repel. Gravitational force is attractive. Yeah, that looks good. And magnetic force is repulsive. That's got to be it, because we have two norths, they'll repel magnetically, and the gravitational force will attract. Let's take a look at the compass. The Earth is a giant magnet. The Earth's magnetic north pole is located near the geographic south pole of the Earth, and vice versa. The reason that is if you were to take a magnet and you want to put it somewhere on Earth, you want the north end of the magnet, of the compass, to point toward the north magnetic pole. So if this is the north end of the compass, it's going to be attracted to the magnetic south at that part of the Earth. So the geographic north pole is the Earth's magnetic south. And the geographic south pole, where the penguins live, is the magnetic north pole of the Earth. And a compass lines up with the net magnetic field. Now, having talked about magnetic north and magnetic south poles, it's somewhat interesting. In actuality, the magnetic north and south pole of the Earth are constantly moving. The current rate of change of the magnetic north pole is thought to be somewhere around 20 kilometers per year, or even perhaps more than that. It's believed that it's shifted more than 1,000 kilometers since it was first reached by an explorer in 1831. That's a lot of movement for what we base all of our compasses on. All right, let's take a look at a problem with the compass in a magnetic field. The diagram below represents the magnetic field near point P. An atom compared to the magnetic dipole moment of a highly magnetized iron bar? Well, the magnetic dipole moment of the iron bar is certainly going to be a whole lot stronger. All right, we know moving charges create magnetic fields, but does it work the other way? Well, yeah, magnetic fields exert forces on moving charges, and we can find the magnitude of that magnetic force, F sub b, is equal to the charge times the velocity of your charged particle times the magnetic field strength, B, times the sine of the angle between the velocity of the moving charge and the magnetic field direction. So the magnetic force is measured in newtons, the charge is measured in coulombs, velocity, meters per second, magnetic field strength in Tesla, and the angle between them, that should be a theta, the angle between the velocity vector and the direction of the magnetic field. Now the direction of the magnetic force, this is going to take a little bit more work. We found the magnitude pretty easily using that formula. The direction of the force is given by the right-hand rule. Here's how that works. Point the fingers of your right hand in the direction of the positive particle's velocity. If it's a positive particle, use your right hand. Point your fingers in the direction of its velocity. If it's moving this way, your fingers go in that direction. Then bend your fingers inward in the direction of the magnetic field. So let's assume we've got a particle going this way, a magnetic field pointing right toward me. I would point my fingers in the direction of the particle's velocity, bend them toward the magnetic field, and my thumb is going to point in the direction of the magnetic force. That's called the right-hand rule. If you have a negative charge, if it's an electron that's moving, go ahead and use your left hand, but the same rules. A mass spectrometer is used to determine the mass of an unknown magnetic field strength. So if we tailor our electric field strength and magnetic field strength just right, only particles at the specific velocity we want will make it directly through here. Everything else is either going to be deflected one way or the other. Let's look at the force on an electron. An electron moves at 2 times 10 to the 6th meters per second. V equals 2 times 10 to the minus 6 meters per second. And it's an electron, so we know its charge is negative 1.6 times 10 to the minus 19 coulombs. Perpendicular to a magnetic field, perpendicular, theta equals 90 degrees, having a flux density of 2 Tesla. So our magnetic field strength, flux density, is 2 Tesla. What is the magnitude of the magnetic force on the electron? Well, the magnetic force, FB, equals QVB sine theta. which is going to be Q, negative 1.6 times 10 to the minus 19 coulombs. Our velocity, 2 times 10 to the minus 6 meters per second. Our magnetic field strength, 2 Tesla, times the sine of 90 degrees. Put all that in my calculator and I find the magnetic force is 6.4 times 10 to the minus 13 newtons. How about the velocity of a charged particle? A particle with a charge of 6.4 times 10 to the minus 19 coulombs experiences a force of 2 times 10 to the minus 12 newtons as it travels through a 3 Tesla magnetic field at an angle of 30 degrees to the field. What is the particle's velocity? Well, we'll go back to our formula for the magnitude of the magnetic field strength, of the magnetic force. FB equals QVB sine theta. Therefore, velocity is going to be equal to the magnetic force divided by QB sine theta, or V equals All right, last question. An electron released from rest in a magnetic field. An electron is released from rest between the poles of 2 bar magnets in a region where the magnitude of the magnetic field strength is 6 Tesla, as shown below. What's the magnetic force on the electron? Oh, here's the key. It's at rest. The magnetic force is going to be 0 since V equals 0. Remember, FB equals QVB sine theta. You only have that force on a moving charge. If V equals 0, then that whole thing is 0. No magnetic force. So our answer, 0. All right, hopefully that gets you a good start on magnetic fields and magnetic properties. Thanks for visiting us at educator.com. Make it a great day, everyone.